In this video, I'm going to be going over compound interest and continuous interest or continuous growth. So compound interest just is the type of interest that we see or that we use when we are dealing with a credit card or a mortgage or any type of financial situation where interest is getting applied. So this is the formula we're going to use. And it's an exponential formula or an exponential function. Here is all the variables, what everything represents. So A of t is the account value at time t. T is the time measured in years. P is the starting value. It's often called the principal. That's why it has a P there. R is the annual percentage rate. And we write that as a decimal. So if we'll see an example, but we always turn the percentage into a decimal, and then n is the number of compounding periods in 1 year. Usually, if it's a credit card, this is compounded 12 times per year, but there's other possibilities as well. So this first example says, if $3,000 is invested in an account paying 3% interest compounded quarterly, how much will the account be worth in 10 years? So we want to know time is 10 years. We want to know what is A of 10 going to be. We have the principal. It's $3,000. The interest rate is 3%, but we want to turn that into a decimal. So this is 0.03. And then quarterly means 4 times per year. So we're going to use an n value of 4. So from here, we just plug everything in. So A of 10 is equal to 3,000. 1 plus the interest rate as a decimal divided by n raised to the nt, so 4 times 10. And then we just can plug this into our calculator to get a value. So you just want to be careful typing everything in correctly. It's often a good idea to use a bunch of parentheses and the order of operations. So what I end up with is $4,045. And when we're talking about money, we usually use 2 decimal places. So $4,045.05. The next example says, for the same account as above, how much will we need to invest to earn $10,000? So here we want to find the P value, and we want, after 10 years, we want this to be $10,000. So what we're going to do is we're going to take this equation right here that we set up, but now we're going to try to solve for P. And 1 plus 0.03 over 4 raised to the 40th. And actually, instead of A of 10, we'll just put in that future value, which is $10,000. All right, so what we need to do is I'm going to calculate the part that's in the parentheses. And then raise that to the 40th. So we get is 10,000 is equal to P times 1.34835, let's say. And then I need to divide both sides by that. So divide both sides by 1.34835. 1.34835, and we get a P value of $7,416.48. So what this is saying is, if we start by investing $7,416 at 3% compounded quarterly, after 10 years we'll have $10,000. Okay, the next type of growth we'll see is a specific type of growth. So compounding growth is always dependent on how many times we're compounding each period of time. But there's another type of growth which is called continuous growth. And this type of growth often occurs when we're dealing with population growth or something that is a natural phenomenon. So if, sometimes we see this in biology where we'll have a bacteria that's growing. So this type of growth is continuous. It doesn't have a set number of compounding times per year, for example. It's always getting compounded. So we use this exponential constant e as a base. So we see that in the base number here. So for all real numbers t and all positive numbers a and r, continuous growth or decay is represented by this formula. And some of the same things are applying. A is the initial value, or sometimes it's called the principal. R is the continuous growth rate per time. And then t is the elapsed time. Okay, so if r is greater than 0, it's growth. If r is less than 0, it's decay. So if r is positive, we're going to see a growth like that. If r is negative, it's going to be getting smaller or decreasing. Okay, so for example, a person invests $100,000 at a nominal 12% interest rate per year, compounded continuously. Now, I'll tell you what, this is not very realistic. I don't think you'll ever find an investment that you can make that compounds continuously, but for the sake of this example, let's see what happens. So $10,000 is the A value. R is going to be 12%, but I'm going to write that as a decimal, 0.12. And then T here is going to be 30. So A of 30 is equal to 100,000 E, and I don't need to put that in parentheses, E to the RT, so 0.12 times 30. Now on your calculator, you have an E button. It probably looks something like this. E to the X, or E to, might have a little box like that. So that's what you want to use. So you can just type this in, 100,000 E to the 0.12 times 30. And what I end up with is 365,9823.44. So this is about $3.5 million, so pretty good. So I would highly recommend being able to find an account that has these settings, because that's a great investment. But like I said, not very realistic. But this next one maybe is a little more realistic. It says radon 222, which is just some chemical compound, decays at a rate of 17.3% per day. How much will 100 milligrams of radon 222 decay in 3 days? Okay, so here T is going to be 3. The R value, well, I need to put 17.3% as a decimal. It's going to be 0.173. We want that to be negative since this is decay. And our initial value is 100, so A is 100 here. So we want to know A of 3 in this case is equal to our A value, E to the R, so negative 0.173 after 3 days. So typing this all in, 100 E negative 0.173 times 3. And I end up with 59.31, and that's going to be in the same unit, milligrams. So that's how much is present after 3 days. All right, and then the last thing is to compare some functions to see if these are linear functions, exponential, or neither. Now, to determine if something is linear, a quick refresher, y equals mx plus b, that's one of the forms. So what's happening if something is linear like this, so linear, we say it has an additive change. In other words, each step of the way, each step down on the function, we are adding the same value. So if I had y equals 3x plus 2, if I make a little table here, when x is 0, I get 2. When x is 1, I get 5. When x is 2, I get 8. When x is 3, I get 11. What we notice is that we're adding 3 each step. Okay, so that's when something is linear. So let's see if we have any of those. So in this first one, that is not linear because I'm adding 9 here, but then I add 15. So it's not the same type of change each step. So it's that first one. F of x is not linear. Here, this looks like I'm adding let's see, almost 10, so 9.75. This is not 9.75. I don't even need to know what it is, but it's more than 10. It's almost, 14 point something. So that also is not linear. This one I'm adding 3, 3, 3, 3. So this one is linear. Okay. So if something is exponential, so similar to how if something is linear, it's an additive change. If something is exponential, it's a multiplicative. Not sure how to spell that. Multiplicative change, which just means we're multiplying by the same thing each step. So here I'm multiplying by 4, but then here I'm multiplying not by 4. So this one, that f of x is not multiplicative change, so it's not exponential. Here, it's hard to tell what I'm multiplying by and if it's the same thing each step. So what I can do is I can divide 29.25 divided by 19.5, and that'll tell me what I'm multiplying by. And if I do that, I get 1.5. So let's see if each step, if I multiply by 1.5, I get the next value. So 1.5 times 29.25 is 43.875 or 43.88. 43.88 times 1.5, 65.82. Yeah, there's a little bit of rounding going on, but I'm pretty confident that that is the same thing. So this is getting multiplied by 1.5 each step. So we would say that this one is exponential. And then f of x is neither exponential nor linear. It could be some other type of function that we can map in one of the special type of functions, but not necessarily.